And then on the bottom, it's everybody who didn't take the drug.
So when we say recovered, we mean that they got back into what we call the normal range, or what is the determination of the term recovered?
Yeah.
referred to?
So this is a kind of a toy example. It's not real data. So it's just a binary variable you can imagine, and you can imagine it's like any kind of disease. And then they recovered means they're normal, and if they didn't, maybe they died. If you want to be dramatic, but you can be whatever you want because it's just for the purpose of a toy example here. Yep, sure. Okay. All right. So looking at this data, you're going to know something very peculiar, right? So for patients that had high cholesterol and for patients who had low cholesterol, if you look within that band, the patients who had high cholesterol, they actually recovered at a higher rate if they took the drug. Same thing for patients who had low cholesterol. But once you add all that data up and you look at the combined, it's the opposite. So this is a statistical phenomenon called Simpson's paradox. Basically, the idea here is when you look at a correlation. So in this case, taking the drug is correlated negatively with recovery. But once I control for cholesterol, so I look in, it doesn't matter which group I look in, that correlation actually reverses. Okay. So how many, based on this data, think that they should take the drug? And how many think they shouldn't? Okay, all right. Well, it's actually a trick question because the answer cannot be determined from that data. All right, so suppose that this was the scenario. It turns out for this particular disease, high cholesterol has a negative effect on recovery. In this case, and not only that, doctors were more likely to prescribe the medication if the patient had high cholesterol. So in this case, the correlation that we see between drug and recovery, part of it is due to this confounding variable cholesterol. Because if you had high cholesterol, you were less likely to recover, but you're also more likely to take the drug because the doctors are more likely to prescribe the drug to you if you have high cholesterol. So actually the positive effect of the drug is mitigated because you're more likely to take the drug if you have high cholesterol, and if you have high cholesterol, you're also less likely to recover. So it's actually, if this were the underlying causal structure that generated that data, they should be taking the drug because you look at the causal effect is within, you want to control for this confounder cholesterol. Does that kind of make sense? So one way you can kind of see this graphically is the correlation between drug and recovery goes both through the direct causal effect that you see on the bottom, as well as through this kind of confounder at the top. And by controlling for cholesterol, I kind of block that correlation due to the confounder. And what I'm left with is the causal effect. We'll get into more detail about how that works, but that's kind of the intuition. So let me give you a second scenario here. Suppose that the drug actually affects your cholesterol level, which in turn affects your recovery rate, right? In this case, do you think we should be taking the drug? So the answer is no, because in this case, we don't actually want to look at the within cholesterol level because we don't want to control for it because we're actually controlling for the effect that we want to estimate. So in this case, the drug has a negative effect overall, but it actually has a positive direct effect, right? So what we see is like within cholesterol levels, if we control for cholesterol, then what we have left is that direct effect. And that actually has a positive effect based on the data that we saw. But if you look at the overall recovery rate, it's negative. And that's because there's a negative effect of the drug that raises your cholesterol level. And by raising your cholesterol level, it actually hurts your recovery chance. So it has a positive direct effect on recovery, but it raises your cholesterol, and then that actually lowers your effect on recovery. And actually, in this particular example, the raising of your cholesterol outweighs the positive direct effect. Okay, so I think, okay, we'll continue. All right, so this is a third scenario. Now, suppose that the drug should not be taken in combination with alcohol, so heavy drinkers avoid it. And in this case, what you actually have is that cholesterol will be correlated with the drug because if you drink alcohol, then you're less likely to take the drug, and you also have it also affects your cholesterol. And then exercise has a positive effect on recovery, but also affects your cholesterol level. So in this case, you're actually going to have correlation between cholesterol and the drug and cholesterol and recovery. Yeah.
So I don't understand these arrows. I thought you said if you drink alcohol, you're less likely to take the drug.
Oh yeah. So the arrows just indicate some kind of causal effect. It doesn't indicate whether it's a positive or a negative effect. Yeah. So in this case, we'll come back to this one. It's a little bit trickier, but by the end, you will know the answer. Okay. So, but these prior two scenarios, scenario 1 and 2, what you saw, right, was that depending on what the underlying causal structure was, you had actually a completely different answer for the causal effect of the drug, right? So if it turned out that the drug had an effect on cholesterol and the cholesterol had an effect on recovery, then the correct answer for the actual total effect was to look at the combined rates. But if it was a different scenario in which cholesterol causes whether you take the drug or not because the doctor's prescription, and then cholesterol also has an effect on whether you recover or not, then you actually want to look at the other one. You want to look at within cholesterol levels. You want to control for cholesterol. And in this case, the drug has a positive effect. So you get a completely different answer depending on what the underlying structure is. And so the thing I want to emphasize here is you can't answer this type of question, like what is the right action to take, unless you actually have some knowledge about the structure. You can't get it purely from data. Okay. All right. So here's another example I'm going to give that shows like how I'm trying to show how the importance of causality when doing data science and machine learning. So I think explainability is a hot topic in machine learning today. There's a lot of concern that, you know, deep learning networks, like they do a great job with vision, they do a great job with NLP, audio transcription and things like that, but we don't really know why. And because we don't know why, we're less likely to trust them and things. So here's just one example to show that how I think causality is a very crucial component for whether we consider an association to be explainable. All right. So back in 1997, there was actually this project to evaluate machine learning in healthcare applications. And one thing that they found out of this study was that asthma was associated with lower risk for pneumonia. So this is contrary to what doctors knew about asthma and pneumonia. What they thought was that asthma increased your risk for pneumonia. But what actually was the underlying structure here was that this data was collected from a hospital. And so if a patient came in with pneumonia, or sorry, with asthma, then they had a higher perceived risk for pneumonia. So the doctors actually gave them more aggressive treatment to begin with. And because of that, they actually ended up with lower risk of pneumonia. So once they had this explanation, they were happy and they were saying, you know, I can use that to inform my decision making. But without this kind of underlying causal explanation, they didn't trust the correlations anymore that they saw. So they actually ended up rejecting neural networks, even though they had the lowest test error rates. But because they need this kind of underlying causal information, which neural networks don't provide on their own. Okay. Here's another hot topic in machine learning today. A lot of concern these days that machine learning decisions may be unfair. I work in the credit card industry now, and an underwriting model needs to be fair with its decision making. There's a lot of legislation about that. So if you apply a blind machine learning model, it may end up like giving results that are correlated with protected attributes. So this is another very hot area of machine learning. And I'm just going to give another example to show how, yeah, go ahead.
What do you mean by correlating with protected attributes?
So protected attributes might be like race or sex. So there's legislation saying that you cannot reject, say, a loan application on the basis of race. And
that's not the model, it's the data.
Right. So I mean, so the thing is, if you may not use that in the data. So you're not actually, even if there is a correlation in the data, we're like legally not allowed to use that correlation to inform the credit decision. So if somebody comes to me and they request a loan, and I look at the race and that I use that to help make the decision on whether I extend the loan or not, that's illegal.
So that's not an input to the model. You can't use it as protected attributes.
Yeah, you can't use it as an input to the model.
You can.
No, you're not
You're
allowed to.
not.
No, no. In fact, you're not even allowed to use like proxies, like for example, location. Certain races will have higher concentration in particular locations. You can't even use location because if you do use location, you're going to have disparate outcome. It's not super well defined at this time, I think, what fairness means from. There's a lot of machine learning researchers who are trying to like define fairness, and I think that the only point I want to get across here is that without like thinking about causality, you're going to have very you're not going to capture exactly what you want out of this idea of fairness. So in this example, they found that there was this 1975 study that found that male applicants were admitted to UC Berkeley at a higher rate than female applicants. But very interestingly, if you looked at within department, females were actually admitted on average at a higher rate than males. So it's the same thing that we saw in the first example. This is Simpson's paradox, where when you control for department, all of a sudden the correlation that you saw before reversed, right? So how can we answer this? Well, you need to understand like, what the underlying causal structure is here. So in this case, it happened that females were applying to more difficult departments to get into. And because they were applying to more difficult departments to get into, in aggregate, they had a lower acceptance rate, even though they actually were getting in at a higher rate. But since they were, more of them were applying to these difficult departments, then their rejection rates were overall higher. So in this case, if you're asking, did UC Berkeley like use gender to determine their admission, then you want to get the direct effect here, and we want to control for the department, right? Because we don't want to account for like the choice of the applicant. And in this case, in this case, they were kind of exonerated from discrimination. Okay. All right. So to bring it back to kind of the relationship between machine learning and causality, I would say like modern machine learning methods, they are able to learn really highly complex associations from data. So they can learn very nonlinear relationships, they can learn high dimensional relationships, and this is what's led to amazing progress in computer vision, NLP, and other classification and purely predictive tasks. But there are clearly limits to inference from purely probabilistic or associational information. And I hope that the examples that I gave prior kind of demonstrate this. And in particular, you're unable to provide actionable recommendations. So you might see that a particular drug is associated with recovery, but if that wasn't conducted by a randomized controlled trial, and maybe the reason why you took the drug could be due to cholesterol, another confounder, then that association is not necessarily causal, right? So without understanding some aspect of the causal structure there, you can't actually tell someone you should take the drug or not. Okay. And then they suffer from a lack of interpretability. So that was the healthcare example where doctors were rejecting the results in neural networks, even though they performed better in terms of error rate because they couldn't get a causal explanation from them. And then lastly, I'll discuss this a little bit more detail, but they also perform poorly in new but related environments. This is another limitation of machine learning today, that there's a very active area of research called transfer learning, where they want to take a machine learning model that's maybe learned in a lab environment or a very closed environment, and they find that actually when they apply that machine learning model in the outside world, it doesn't work well because there was some differences in the data, in the distribution of the data. Okay. All right, so hopefully now, like, we all agree that causality is important. So let's move on to what is causality.
I'm sorry, what's the connection? I mean, you brought up these topics of
Yeah.
transfer learning and interpretability. What's the connection to causality?
Yeah, so I think with interpretability, right? I think it's often the case that just because you see a particular association, if you can't explain it, provide a causal explanation, then it's not maybe something that you necessarily trust or you find interpretable. So for example, like if you these doctors, when they did this study, they found that a lot of machine learning algorithms learned this correlation that asthma was associated with lower risk for pneumonia. And this was like very unexplainable to them until they got this causal explanation. Oh, it's because when you have asthma, then doctors will be worried that you're going to get pneumonia, and then they actually take preventative steps, and it actually ends up lowering the risk of getting pneumonia. So once you have this underlying causal explanation that explains the correlation, that you got, then a lot of people feel like they have a satisfying explanation.
Causality is not coming from, it's coming from biology. It's not coming from stats or machine learning.
Right. Well, okay. I think we'll get into that a little bit more on like what I mean by causality. Yeah. All right. So what is causality? So we're going to be using this paradigm called structural causal models, and it basically makes this assumption that that whatever data you have was generated by a series of what we call structural equations. And these structural equations represent like a physical mechanism, like biology, for example, that generated the data. Now, I might not know specifically what that data is, but I assume that they're like that, for example, in this example here, recovery is a function of cholesterol and the drug, right? As well as other factors. That's what the use of R there is. It represents other unobserved causes that I don't have data on. So in this case, that function is actually a deterministic function of the causes of the outcome here. So if you say, yeah, so let me slow down a little bit. So here we have R, recovery, is a function of the causes that we have modeled, cholesterol and drug, as well as a bunch of unobserved causes. Now, if I saw all the unobserved causes, what this equation says is I would know exactly what the value of recovery is. So think about if you flip a coin, then we kind of think of a coin outcome as random, as 50-50. But that's only because I don't know the initial velocity at which I launched the coin, and I don't know the rate at which it's spinning. But if I knew those two variables, I would actually know exactly the outcome of the coin, right?
So are the unobserved causes or the unobserved random variables, are they normally distributed random?
Not necessarily. I mean, if we make certain assumptions like that, it can help us do inference. But in this model that I've put out here, I'm not actually making any assumptions about the distribution, and I'm not making any assumptions about what that function f looks like. I'm just saying that it's there. Yeah.
In the second equation, shouldn't it be f of t?
Oh yeah, that's a typo. Good point. Yeah, that should be a C. Thank you. Yeah, it's a typo. Yeah. Yeah. Go ahead.
Are we still talking about stochastic though? When you mentioned the first model, the U are,
Yeah.
is that like an error rate or an error term?
Yeah, so that's an error term that represents all of the unobserved causes. And then because we don't observe them, we assume it's a random variable. And that's what generates the probability distribution over the data. Okay, so I'm going to give a physical example here, an example from physics, where suppose you want to predict where a cannonball will land based on the initial angle of launch. So the machine learning approach here would be to collect a whole bunch of data where the cannon had different initial angles, and then you observe the distance, and maybe you could apply like a machine learning algorithm, some kind of nonlinear regression, and you would be able to do this prediction, right? But what the structural causal model paradigm is saying is that underneath that data, right, what generated that data was this physical equation here. This is the structural equation. So it's the distance equals, this is Newtonian. I solved this from Newtonian mechanics, right? It's equal to some function of the velocity, the initial velocity of the cannon, of the cannonball, the angle, as well as the gravitational acceleration, right? Now there's also your error term here. I could, and that error term could be like due to other unobserved factors that I'm not modeling, like maybe there was some wind or there's some air resistance or whatever. And that kind of like may result in some a distance that's not exactly what is computed here, right? So this is kind of the underlying structural equation. And if you see like the kind of what I can do from this structural equation that I couldn't do from just a regression is I can predict the effects of actions, right? So I could say like what would happen if I improve the initial of the cannon and increase the initial velocity? I could tell you what the effect of that action would be. I could tell you like what the outcome of cannons and how to predict the distance of the cannonball in general, even on other planets. I could say, you know, let's say I move to Mars, I can just change the gravitational constant and I get like answers there. So there's something like much more invariant about this equation than what the regression learned. And that's why there's been a lot of work that's trying to use causal relationships to help with transfer learning. And then lastly, this is the part about interpretability. It not only describes the distance, right? So the regression you can give it the input of theta and it will predict where the distance will go, but it doesn't really explain it. Here I can answer questions like, why did the cannonball land 60 meters away? And then I could say, well, it's because we were on Earth that has 9.8 meters per squared, gravitational acceleration. It had this initial velocity and this angle. That's exactly why it happened. And that's a very, very satisfying explanation.
There's no effect of altitude at which the cannon is sitting.
Yeah, so I'm assuming it's flat here, but we could add that as could be another input to the structural equation.
And
Yeah.
temperature and air pressure.
Yeah, all could be, at the moment that would maybe be part of the U, because those are unobserved other causes, right? These are all these unobserved other causes that I don't explicitly model. So I can say that's random because I can't observe it. And then that's why sometimes this is not exactly what I predict. But I could also explicitly model it and then I would have more precision. Yeah. Okay. So now I'm just going to give a comparison between like traditional statistical inference versus causal inference. And most machine learning methods today, what they really do is like statistical inference, or just learning this association in the data, but they're not really taking into account causal information and they're not really making causal inference. And so what you have is like this assumption in the traditional statistics paradigm that generating your data, there's some kind of joint probability distribution. And then there's all kinds of like statistical techniques for estimating aspects of that joint probability distribution. So maybe that's the mean. Maybe I want to know the mean. Well, I know how to estimate mean. I just take the sample average, and that's a good estimator of the mean. And there's really well understood properties of that in the statistics literature. Or maybe I want to know the joint distribution between two variables, x and y. I could do a regression. Or maybe I want to learn like some kind of correlation between an image, like the distribution of a bunch of images, and whether it's like a dog or a cat. Then I can train a neural network, and it learns that this kind of like decision boundary that's an aspect of that joint distribution. Okay. Now, causal inference in the structural causal modeling paradigm, what we actually assume is that there's an underlying data generating model. So that structural equation that you saw there previously, that generates the joint distribution, right? You have this deterministic structural model, and then you have a random variable that goes into it, and that generates the joint probability distribution, which you get from the data. And what I really want to know are aspects of M. So when you do causal inference, I want to know like all of these kinds of questions here, right? Like, what if I want to predict the effect of an action? Then that's something that is an aspect of this underlying structural equation, right? If I just wanted to say do prediction, then I would probably be okay with the joint distribution. And I'll talk about that a little bit more later. All right, so how can we estimate causal quantities? Yeah, go ahead.
Example, if you collected enough data, even data maybe on different planets, I don't understand what you're really missing by just, I mean, why doesn't the raw data kind of tell you exactly what that equation would be?
Yeah, so if you did collect data on the gravitational constant and you move that around to different planets, you would be able to estimate. You would be able to predict the distance of the cannonball on different planets, but you would have to actually collect data on different planets to do that, right? So in this case, like I don't even need data from other planets, right? So I can do this transfer learning, which is one of the things that people are very concerned about with machine learning today. So for example, like you see these reinforcement learning algorithms that learn to play Pong really well. I think I saw a paper where they trained this algorithm to play Pong, and it did really, really well. And they make some like minor change to the data, like they changed the scoreboard's font, and all of a sudden it can't do it anymore. So there's like a lot of yeah, it seems kind of silly, but there's a lot of limitations when you just make minor changes to the underlying distribution, and all of a sudden it just doesn't perform anymore. Okay, so how can we estimate causal quantity? All right, so the problem this is in the literature, we call this problem identification. How can we take a causal quantity and relate it to the joint distribution? Because the joint distribution is actually what's estimated from data. But I'm gonna introduce this problem using an example. I think that'll make it more understandable. So okay, so there was a study in 2011 where they found that eating red meat was correlated with colorectal cancer. But the real question I want to know, right, is not just is it correlated. I want to know if I should eat less red meat, and if I eat less red meat, will that reduce my probability of getting cancer? So it turns out that red meat consumption is correlated with other dietary risk factors. So people who eat red meat, they're less likely to eat lots of fruits and vegetables. They're less likely to exercise. So there's also associated with various behavioral risk factors. And so you have to ask the question, like the correlation that I'm seeing between those who eat a lot of red meat and getting cancer, is it because of the red meat, or is it because they don't exercise as much? And it's because they eat other foods that are bad for you, right? And in this case, if I only collected data on red meat consumption and cancer, I can't answer the question. Because so you can see here in this graph, let me take a second to explain the graph down there. What that's saying is that there are unobserved common causes of red meat consumption and cancer. So food preferences is one unobserved common cause, right? If people who have preferred to eat red meat, they also prefer to eat other fatty foods, and they prefer to drink more alcohol, and maybe that's what's causing the cancer. So I have this unobserved confounder that's also generating some of the correlation that I'm seeing, at least some of it, right? And because I only have the correlation between red meat and cancer, I can't distinguish how much of that correlation is due to the causal effect and how much of it is due to the confounding. Okay. So in that case, we actually say that the causal effect of red meat on cancer is not identified. And here I'll also introduce a little bit of notation. In the lower right, that's the probability of cancer given that I do red meat. So like I eat more or less red meat. It's different from observing if somebody ate more or less red meat, right? Because if I observe that someone ate more red meat, they're also more likely to not exercise, and that will increase their probability of cancer. That's your standard conditional expectation. But if I say, if I say force you to eat less red meat, then that has nothing to do with your fruit and vegetable consumption or anything else. And that's actually the causal effect, right? If I take that action, I want to know the actual causal effect of not eating less red meat, not the association that's due to, say, smoking more or exercising less. So that's how we write it mathematically. Okay. All right. So in this case, it was not identified because we couldn't distinguish how much of the correlation was from the direct effect and how much of it was due to confounding. However, if you actually collected the data, right? If I collected data on their dietary risk factors in general, like how much of the other things that cause cancer that they eat, if I collected data on the other behavioral risk factors, like how much they exercise, whether they smoke or not, how much alcohol they drink, then I can control for them actually, right? So I can look, for example, let's say, to give some intuition here, let's say I looked only at people who exercise the same amount, right? Now, any correlation I see between red meat and cancer is not going to be due to the how much they exercise anymore, because I'm only looking at those who exercise amount. So I'm controlling for it. That's why they say that. So in this case, if I were to control for dietary risk factors and the other behavioral risk factors, then all the correlation that's left is due to the causal effect, and I can identify it. So this is what we mean by identification. And once it's identified, I can estimate the causal effect. There's various ways to do this sort of controlling via estimation, and here's a few examples. There's something called propensity score matching. So I missed that in the slide. Sorry about that. Inverse probability weighting. And if I assume that like some kind of functional form for it, I can use regression. And in that case, I would just add those factors to the regression. So say these were, so if I, for example, I could do a logistic regression, and if I wanted to control for dietary risk factors and behavioral risk factors, I would just add those variables into the regression, and that would be one way to do it. Okay, so how do I actually know whether controlling for a set of variables will allow me to get the causal effect. So I kind of like, I think earlier I was kind of giving some intuition about, so let's give a simpler example going back here, right? So I was saying like, you know, there's correlation that's due to this direct effect from drug to recovery. And there's also correlation that's due to this path through cholesterol, right? But what I really want is the actual causal effect here. And by controlling for cholesterol, right? If I only look at people who have high cholesterol, that's no longer a source of variance. And what's left is the drug and the recovery. And I actually like block the association that was generated through the confounder. And so I'm going to make that a little bit more explicit here and say exactly how you can determine whether a path is blocked or not. Okay, so a path is just any way of moving through along these like arrowheads to get from one variable to another, right? And if you look on the left, okay, sorry. So if you look on the left here, you can see that correlation is passed along through two types of paths, right? They can go through like direct arrows like this, but they can also go when the two tails are touching each other. That's how like correlations pass through confounding. So this is a common example of, you know, correlation doesn't imply causation. Ice cream sales are correlated with drownings. Why are ice cream sales correlated with drownings? Because when the weather gets hot, people eat a lot of ice cream and they also go swimming, and so they're more likely to drown. However, if I only look at hot days, right, then you're not going to have then they won't no longer be correlated because that reason for the correlation is gone. So if I take the correlation of ice cream sales and drownings given temperature, there won't be correlated anymore. So you can see that that path is blocked. Same thing if I control for water activities, right? If I only look at days where the number of people swimming is the same, then you're not going to see this correlation anymore. So that path is blocked. So if the arrowheads come together, if they collide like this, so we call that a collider, then there's no correlation that passes between it. So you can think of it, this example here. Say you have an alarm at your house, it goes off when there's a burglary, as it should, but it also goes off when there's an earthquake, right? Now, they both cause the alarm to go off, but those are two independent events. Burglary and earthquakes are independent. They cause the alarm to go off. Like, there's nothing about this causal relationship that generates correlation. But interestingly, if you actually control for alarm, then they become correlated. So the intuition behind this is if the alarm goes off, right, and I know there was a burglary, then it's less likely that the reason it was because of an earthquake. Vice versa, if I know that the alarm goes off and there was an earthquake, then I know that it probably wasn't a burglary happening. So if you go back to the definition of conditional independence, right, knowing one thing, if it changes the probability of the other, they're actually dependent. So if I control for alarm, I actually generate correlation between burglary and earthquake. And also, if I take like an effect of the alarm, like police arriving, that also has the same. It will also generate correlation between here and here for the same reason, right? So let's say that the police arrive, and I know there was an earthquake because whenever the alarm goes off, police arrive, then it's less likely there was actually a burglary. It's just an indicator of whether the alarm went off or not. So it's the same idea. Okay. So this is the backdoor criterion, and it's a graphical criterion. So you use the graph, and using the graph, I can tell you whether or not a causal effect is identified by controlling for confounders. So how can I do it, right? So if you go back to this example, if I can block all of the paths except the one I care about, then I've done what I wanted, right? So if I control for cholesterol, then all that's left, the only path that's still left between them is the one I care about. So I'm able to actually identify and estimate the causal effect by controlling for cholesterol in this case. There's a couple caveats here, which is that you cannot control for anything that is an effect of the drug. You cannot control for say like there was some kind of another thing that indicates recovery, like somebody goes home happy or something, then you shouldn't control for that. So that's the only caveat there. And then this is the other example that we saw before. So if we look at all of the what we call backdoor paths between rennie consumption and cancer, right? they are all blocked if I control for D and if I control for B. Because I look at this path here is blocked here, and then this path here is blocked, this path here is blocked here, and this path here is blocked. So the only path that's left if I control for D and B is this one. Okay. So now going back to that original example, which I said you would be able to solve by the end of the talk. Here, do we want to control for cholesterol or not? The answer is we actually don't, right? So if I control for cholesterol, you remember that I said that if it's a collider, it actually induces correlation. So if I control for cholesterol here, then there will be confounding that I've generated. And so the actual right answer, if this were the underlying causal structure, is to look at the combined data and not to control for cholesterol. So this is actually like, this is pretty unintuitive for a lot of people who who kind of study causality, because people often in the past, people have defined a confounder as something that's correlated with the treatment variable, the X variable that you want, and also correlated with the outcome variable. So, but that's the case here. Cholesterol is correlated with both recovery and it's correlated with the drug, but I still shouldn't control for it, and it's not an effect of the thing I care about. So there have been people who have in the past have defined confounding as something, a confounder as something that's correlated with the treatment, correlated with the outcome, and also not an effect of the treatment. But this satisfies all of those things, but I still shouldn't control for it. Same thing here. Suppose that that these behavioral risk factors was also confounded with cancer. There's some other latent common cause that both causes you to engage in whether these risk factors and also gives you cancer. In that case, I shouldn't control for B. And in fact, it's not identified at all, because if I control for B, I open this collider path here and I induce confounding. But if I don't control for B, then I have this guy here, right? And I have confounding too. So it's actually not identified, and I cannot estimate the causal effect in data at all if this were the underlying causal structure. Okay. Yeah. Okay. So this idea of estimating a causal effect by controlling for confounders, this is like the most common way of trying to estimate a causal effect, and it's something that people have been doing informally for probably since we've discovered correlation. And then one day, this guy named Simpson found that you can actually completely reverse your correlation when you control, and it was very confusing. So yeah, sorry. To go back to that example, you really have to be careful and explicitly model the underlying causal relationships if you want to be able to estimate a causal effect. So this idea of controlling in order to estimate causal effect is just one identification technique. There are other ways that I can estimate causal effect besides controlling for confounders. And one of them that's very common is called instrumental variables. So this has been known and used by economists since like the 1920s and other scientists as well. But it was originally attributed to an economist. Yeah, so I'll explain how this works. So suppose I wanted to estimate the causal effect of veteran status. Like if you served in the military, does that have a positive or negative effect on your future wages? So it could be that, but those years you spend in the military could have been years you were training for a job or going to college, and maybe that results in lower wages. So this is like a question of interest to some economists. But the thing is, like, whether you actually go and serve in the military is clearly confounded, right? Like if you look today, people who serve in the military are less likely to have to come from like more wealthy socioeconomic groups. So there's other confounders there that will affect whether you go to the military and will also affect your future wages. So the correlation I see there is not going to be entirely causal. So one way I can still get the causal effect is using what we call an instrumental variable. So in this case, you can see like if I look at whether people were drafted into the military. So the draft is basically random, right? Like it's based on your birthday. It has nothing to do with your socioeconomic status or anything else. And it has no direct effect on your wages except whether you served in the military or not. So you can see that there's no confounding variable between the Z and the Y here, and there's no direct edge here. So I can look at the causal effect of being drafted on your future wages, and that's not confounding. So like I can clearly get that. And then from that, I can extract the effect of veteran status. So so that's like intuitively how it works. I won't go into the math here. Actually, I can probably do it. So assume that these relationships are linear, right? So then the covariance you can actually is referenced. Okay, actually, yeah, actually I won't go into it right now. We can come back to it if people are curious if there's extra time. But how can I determine whether a variable is an instrumental variable? What I do is I remove this edge here, and I now check to see if now there are no open or active paths between the instrument and the outcome variable. So if I were to remove this, you can see that Z is actually separated from Y, right? There's no active paths because the only path left is this collider one. So the colliders don't pass on, are not active, right? So I can see that if I remove the edge for beta here, then Z and Y are now separated. And that's how I can determine whether a variable qualifies as an instrumental variable. All right. So the other thing I can do is if it happens to be the case in this particular example, so suppose that I want to estimate the effect of a training program on future earnings. This is also probably confounded because employees that attend the training program, maybe they need training more. They're not doing so well. So like, oh, I should go get training, right? And because they weren't doing well before, that also means that that'll affect their future earnings. So this is clearly, you can't just look at the correlation between the two and then say like people who attended the training program had higher earnings, and that was because of the training program. What I can do is use something like proximity as an instrumental variable. So if proximity affects the proximity to the training program, let's say the training program is in the office, maybe I attend the training program more because I'm close to it. Whereas if I live far away, I might not stay late at work to attend the training program because I still have to do this long commute, right? Now here we also have an extra path that we don't want to have here. So if you remember the condition that I gave, it was if I remove this edge, are they separated? The answer is no, right? Because there's this extra path here and they're not separated. But if I actually control for W and I condition on it, then they are separated. So I can actually still estimate it in this particular case using an instrumental variable. So it doesn't have to be separated at first, but if I can control for something and then separate it, then I can still use this instrumental variable. All right. Just to now, so a lot of so instrumentals are very, very commonly used, and usually people don't explicitly check if they're true using graphs. And I'm going to give a couple examples to show like why using a graph can be really, really helpful when you're trying to decide whether something's an instrumental variable. So here, like, let's suppose that the efficiency of the workers also affects both the number of hours you spend working, the amount of time you spend in the office, and it also affects your earnings, right? So then that's this unmeasured confounder here that affects both. So I draw this edge here. In this case, I can no longer control for W and have Z be separated, right? Because I create this collider here. So now I can't identify the causal effect and I can't estimate it again, if this were the case. But I'm going to give a different scenario. So like suppose that this is a high-tech industry and workers can easily work from home. And in this case, you know, it doesn't matter how much time you spend in the office, and your proximity doesn't really matter either, right? So here, there's no more direct effect from time in office to here because you could just work from home. And in that case, I can use proximity as an instrument again, right? But I can't control for it. I should not control for your time in office because this is a collider. So if I control for W, then I'm going to induce extra correlation here that I don't want. Yeah.
I'm a little confused by the difference between the double-sided lines with an arrow on each end versus the one with an arrow on one end.
Yeah, so if there's a double one like this, that means there's a common cause, something that's causing them both, but I don't observe it. Like, so in this case, it could be like I think here, I had it as efficiency, right? So this is the efficiency, is an unobserved cause because I didn't measure the efficiency of workers, so I can't control for it. But it is acting as if there was a common cause here. So that's how I represent that graphically. The edges like this, that just represents, that means that W is a cause of Y. And then X is a cause of Y, Z is a cause of X. Okay.
I thought you said the direction of the arrow, it could be a positive or a negative correlation.
That's right. So it could be, so when we say that, X causes Y, it just means that Y is some function of X. It could be a negative function or it could be a positive function.
So it either causes it to go up or causes it to go down.
Yes, exactly. Yeah, as opposed to not causing anything. Yeah. So this is the last example. Let's say that that worker efficiency also affects whether they attend the program, because less efficient workers are more likely to benefit from the training. In that case, you have efficiency as a cause for time in office and the training program, and we add this latent confounder there. And in this case, once again, you can still use it as an instrument. You just can't control for W. So that's it. Because this path here, it's a collider. It doesn't actually induce any association. And same thing here. All right. So this is like a basic causal roadmap, I would say, when you want to estimate some kind of causal quantity. First, you need to define the causal model, right? Like what we saw in the very first example was that without the causal model, you couldn't know whether the drug helped or not. And the way and the evidence of that really is the fact that different causal models actually give you completely different answers, right? So if you don't know what the causal model is, it could be that one is true, that causal model A was true, and then that means that the causal effect was positive. Or it could be that the scenario 2 was true, and then the causal effect was negative. So I really need to know something about the underlying causal structure before I can estimate a causal effect or any kind of causal quantity. The first step is to define that causal model. In this case, we used graphs over the available data, and then you want to express the query as a causal quantity. So for example, going back a bit here, I expressed, I wanted to know the probability of cancer given that I do eat more red meat or I do eat less red meat, and that is expressed in the graph here. Okay. I'm getting a, oh, there we go. Okay. So the second step is to identify the causal effect. So I went over like two common identification techniques. One is when you control for confounders, right? So that's one way to identify a causal effect. In some cases, it's not possible to use that technique, or it might not be possible at all to estimate the causal effect. But we need to see how to actually estimate the causal effect using the causal model, using the causal knowledge that I have. Another example is using instrumental variables. So if I knew that this was the underlying causal structure, I can actually estimate the effective training program using instrumental variables, which is the identification technique. The last step is estimation. So I briefly mentioned that if the backdoor criterion is satisfied, so if I can control for confounders, I can estimate the causal effect using, say, regression, or I can use a couple other estimators that I didn't really discuss in detail, but one's called inverse probability weighting. There's another called propensity score matching. If it's an instrumental variable, the common way of estimating the causal effect is something called two-stage least squares regression, right? So there's OLS regression, but this is a different type of regression where what I actually do is I would regress X on Z, and then I use that regression to estimate X, right? So I get this, like, let's say it's a linear regression. So I'll regress X on Z, and then I get this regression coefficient, we'll call it beta. Then I take beta times Z for all the thing, and I get this estimate, like an estimate of X. Then I regress Y on the estimate of X and not the actual X. And that's what they call two-stage least squares regression. Okay. All right. And I just wanted to point out this last quote by a computer scientist or philosopher named Nancy Cartwright, which is no causes in, no causes out. So without having some kind of underlying causal knowledge, I'm never going to be able to make any causal conclusions. And I hope that's somewhat clear now from the examples. Okay. All right. So lastly, I'll go over some real world examples that I worked on at Brex. So the first one is around reducing global limit declines. So Brex's first product was a corporate card for startup companies. We've since expanded our product offerings, but that's what we started with. And we had a lot of success early on because most banks are not willing to lend to startups because they're new, they're risky, and instead they would lend money to, say, the founder if they had a great credit history, and they would be personally liable. So when we started Brex, the thought was like a lot of these startups actually have a lot of money in the bank, right? They've raised money from a VC fund, and some of them have like millions of dollars in the bank. So we should be able to lend the money if they have millions of dollars in the bank. What we do is we have an active connection to their bank account, and every day we just check how much money they have in the bank. We look at all their bank account transactions, and we use that data to assess their risk. So there's this concept that we invented called dynamic underwriting, where we check that every day and we re-underwrite them, and that's what really keeps us safe, right? So this could, because we do that, and their bank account might change every day. They might like spend a little bit, or they might do something, and that could actually result in a limit change, at least with our first underwriting model. So this is really good for Brex in that it keeps us safe. Like, anytime we see that you have a lot, like not a lot of money, we can even cut off the credit and initiate the collection. But it's not great from a product's perspective because if you have a credit card, yeah, go ahead. Yeah, I'll go into that. Yeah. So it's not great from a product perspective because every day, the amount that you can spend can change. So you can't really do your spend planning very well if in a week your spending limit may drop. So a global limit hit or decline is when we decline a transaction because they've reached their limit, right? So you have a credit limit of, say, $100,000. Let's say you spent $99,000. Now you want to make another $50 let's say $500 transaction. We'll decline that because we're only willing to give you $100,000. Okay. So because these limits, so we had this question, like how much was our daily limit changes driving these declines? Because this is a bad customer experience, and we want to kind of look into better what's causing it. All right. So the nice thing about doing this is I know exactly what the causal graph is because I know what's setting the limit. We established that policy, so I know how which risk factors actually cause the limit change. So that's why I can draw that arrow from W to L, and I know there's no confounding, right? There's no hidden variable there that is acting as a confounder because I know all the possible variables that are causing the limit because that's according to my policy. And then a decline happens as a deterministic function of how much they spend and how much their limit and what their limit is. Whenever the spend exceeds the limit, then you get a decline. So I know exactly what the causes of a decline are too. So now the thing I don't know, right, is exactly like the relationship between risk factors and spend. Because if a customer is risky, it may affect how they spend. They may be more desperate for money, so maybe they spend more, or maybe they'll get more frugal, they'll spend less. That part I don't know. There's all sorts of confounding factors here that I can't account for, right? But I can still get the causal effect of limit changes on declines, right? If I go back to the backdoor criterion, if I control for these risk factors, all of which I can observe because these are the risk factors that I use to set the limit, if I just control for those, then I block all of the confounding association, and I'm left with the causal effect. All right. Yeah. So that's kind of it. So the way we did, so the way I estimated it in this particular case was using a regression. So I did a logistic regression of y on the limit, the risk factors, and the spend changes, and then that kind of is a consistent estimate of the causal effect. And what we found was that changes in spend behavior had little effect on declines, and instead it was actually it was actually dynamic underwriting and the limit drops that were causing the declines. So this is sort of yeah, it was like a flaw in the product because they were spending as they always spend, and instead it was because of we didn't do a good job assessing their risk beforehand and giving them a steady limit, and so we had to change it all the time, and that's what was causing the drop or the decline. Sorry.
We have one comment.
Oh yeah. Okay. How do yeah, go ahead.
You need to repeat.
Okay, sure.
How to identify the causal structure from observed variables and target variables, especially when perturbation is not visible?
Sorry, can you repeat the last part?
Perturbation.
Perturbations. Oh yeah, okay. So that's a good question. The question was, how can I learn the causal structure, right? When I can't actually perturb the variables myself. And the answer is you can't just from data. You can learn something about the causal structure, but you can't learn the full causal structure. In this case, I didn't learn it from data, right? I didn't learn this causal structure from data. I knew what the causal structure was because we generated this data ourselves. Like we decided the limit policy. So I know what causes the limit. And we know what causes a decline, like it's part of our policy as well. If you exceed your spending limit, we will decline the transaction. But I didn't know, like exactly this relationship here between risk factors and spend. So in that case, I had extra knowledge. If I didn't have that knowledge and I was only trying to learn the structure from data, it's not really possible. So for example, like if I see correlation between X and Y, then I don't know if X caused Y. I don't know if Y caused X, and I don't know if it's generated from a confounder, a common cause, right? But what I can do is I can learn a little bit about the structure from data. So if you can think of a scenario where, like, let me go back a bit. Let me see if there's a good example. Here, okay, this one's a good example. So if I look at this one with the ice cream sales, temperature, water activities, and drownings, there's certain things that I can find in the data that would tell me something about this underlying structure. So in this case, it's because ice cream sales is uncorrelated with drownings if I control for temperature. So that's something I can learn from data, right? I can learn the correlation matrix over the variables, and I will see that the correlation for ice cream sales and drownings actually disappears if I condition on temperature. So that tells me that there's no direct causal link between ice cream sales and drownings. Because if there was, there's no way for me to make it disappear. So, but it doesn't tell me from data, like if, let's say that actually, drownings cause water activity. No, that's a bad one, sorry. Let's say that water activities cause the temperature, which is not true, but if that were the case, you would have the same kind of, you could generate the same data. So I can get to learn something about the causal structure, but I can't learn everything. That's the idea. So what we say in the causal inference community is like you learn an equivalence class of possible structures that explain the data, but you can't distinguish between those different graphs in the equivalence class. Okay. Going back. Okay. So after we found this, we actually implemented some changes to the underwriting policy. This is a second example of a causal inference problem that we worked on. And so we came up with a new underwriting model and a new automated underwriting policy. But we wanted to assess how much this policy would help. Does it have a negative impact on risk? Does it lower our revenue because the customers spend less? These are typical sort of like questions that you would normally use an A/B test to run, right? But yeah, just to go back a little bit on A/B testing, this is probably like one of the standard ways in tech companies today for estimating causal effect. Because if you run an A/B test, you're not going to have any confound. Like let's say I ran an A/B test on limit changes, right? And I just started randomly changing limits around, then it won't be due to risk factors anymore. And the only correlation I see between limit changes and declines would be due to the causal effect. Like this, I basically eliminate this edge between risk factors and limit, and then I'm just generating L instead from a coin toss, excuse me, essentially. So that's the standard way of estimating causal effects, right? But in this case, we didn't want to do that because we wanted to minimize the negative impact that we had to customers. So we actually we did a kind of essentially a biased A/B test where we made it a higher probability of selection onto the new policy if that new policy was more likely to work for you. And we had various criteria for how to determine that, but we basically biased it for ones that it would work better for, and then lower probability of selection if we were worried it might actually negatively impact you. So normally this would be this would mess up your whole A/B test, right? You wouldn't be able to actually get the causal effect. But I can actually control for this bias because I made that selection mechanism. So there's now a selection mechanism that determined which policy you got. And yeah, the selection mechanism maybe actually should be more of like a latent confounder one. Yeah, the double-edged one, but the selection mechanism may be correlated with the outcome, like less customers that are less risky, maybe they were more likely to be selected in one policy or another, and that affected the outcome. But since I know this structure, I can then control for the selection mechanisms, and I can actually still recover the causal effect. All right. So that's basically the talk. I have some recommended reading here. If you want to learn more, if you're intrigued by causal inference. The first one is my advisor's most recent book. This is probably the easiest one to, this is like the most enjoyable to read, I think. It's like, it's kind of written as like a pop science book. So it's like, has a lot of history and storytelling there. It's not too technical. If you want to get a little bit more into technical, there's this second book by my advisor, Causal Inference and Statistics, which is basically a textbook written at maybe a college or early, like first year grad school level. And then just so I have another book here is this written by economists. It's called Mastering Metrics. And yeah, just a little bit blurry here, but it says Mastering Metrics, the Path from Causal Effect. It's by Angrist and Fishke, I think. I don't know how to pronounce it, but you can find it online. And here, there's some code that goes with the book. So there's like a lot of code if you want to see that. Causalfusion.net is my is a collaborator of mine when I was in research. He's now a professor of Columbia. He developed this software. It's still in beta testing, but you can register for beta testing. And then lastly, PyAgram is like a Python package that actually implemented a lot of the examples in the Book of Why. So yeah, that's basically it. All right. I'm going to finish by letting we are hiring all sorts of people. We're growing very quickly. I think we had a $2.6 billion valuation in just over 2 years, so like very rapid growth. I've been there for a year. When I joined, it was like 80 something people, and now we're over 400 after a year. So a lot of growth, exciting place to be. So check out the careers page if you're interested. Yeah. And is there any other questions that you can take them, or do we still have time for questions? Or yeah, I know a lot of people ask questions during the talk, so that was great too. Yeah.
What is the symbol that's two vertical lines with a horizontal line underneath?
Two vertical lines. Did I have it in here?
Yeah.
Okay, let me see. Where was it? Oh, independence. Yes, that's independence. I'm sorry, I didn't. Where was it?
Right there. Go forward.
No, back.
Okay. It is independence.
You just passed it.
I did again.
No, you just
Ah, yes. Oh, I'm sorry. Yeah. This is independence. So the idea was, I was saying like kind of intuitively that these bidirected edges here, they represent latent common causes, right? They're like common causes that I don't observe. And if you go back to like the structural model, if you remember, like the error term here represents all unobserved causes of the thing. So like, let's say here we have F and B. So F is caused by, I mean, I don't observe any common cause. I don't observe any of the causes of F. So I only have the error term here. And then I don't observe any of the causes of B. So I just have the error term here. So there's actually a common cause. And that means that these two error terms are not independent. And that's where the independent assumptions come in. So like there's an independence assumption that there's no common cause between B and C. So it's just saying that, so like this here, this use of C is independent of use of B. That's another way of saying that there's no common cause between them. That's an assumption I'm making, or I have knowledge of that. Yeah.
Would you say more about propensity score matching inverse probabilistic rating and regression? I would have.
Yeah. So
you use the distributed regression to get propensity matching.
No. So once I like, so here I can estimate the effect of red meat on cancer using by controlling for these confounders, right? So what you could do, one way to do it is to literally look at the correlation for all of the different values of D and B, right? So I can look like for people who have good dietary practices, who have bad dietary practices, and I look at the correlation, how that changes. And then once I want the total effect, I just average over them again. So it's just like, I take a weighted average. That's one way to do it, but they're to estimate the causal effect. These are like more efficient estimators. There's like kind of better ways to do it than that. I won't, so propensity score matching, what it kind of does is it'll take the probability for different, so for every individual in the study, right? There's a different probability they eat red meat. And I take that probability and then I match them on that. And then, so I basically control for the probability that they eat red meat, and it has the same effect in large limits as like, as the data goes to infinity, it has the same estimate. So it's still a consistent estimator, but it actually will perform better when you have smaller samples. So yeah, that's the idea.
But how do you get that probability then? Do you use like just regression, or should you then regress about the variable?
Oh, that's one way you can do it too. Yeah, that's right. But when I put regression here, I kind of meant that you could actually regress C on R, D, and B, and that'll give you the causal effect, as long as the associations of the data match the regression specification you have. So if it's a linear regression, then those relationships have to be linear. Otherwise, you're going to get bias due to misspecification as well. Yeah.
You say when it works on doubly robust.
Doubly robust. Yeah, so that's another type of estimator. I don't know too much about that. I know that it's like it's a certain way to like estimate when you have these assumptions satisfied for causal inference. That is robust to like particular types of errors. But yeah, I don't remember the details on that. Yes, my area of research was more on identification when I was in research, and less on estimation. So yeah. Yeah, go ahead.
The query of interest, when we change R, what do we do with the rest of the variables?
What do you do with the red? Oh, so this is what I care about, right? I want to know the effect of red meat on cancer. So I want to take this causal quantity and figure out how to estimate it from the data. So this is what I want to know. Does it make sense?
Yeah, but don't the other factors also make a difference? Even if we deliberately affect red meat consumption, different other underlying factors, shouldn't those change the probability?
Yeah, okay, yeah, so like, that's right. So when I want to estimate this quantity, it'll be like, if I say what this is equal to, I need to control for them. So this is, so I could compute this, right, by looking at the probability of C given D and B, and then basically averaging that over, so yeah, I can get the probability for within levels, like, for people who have good dietary habits and have good other behavioral habits. And then that's kind of a causal effect for those particular people, right? But then if I want the total effect, I just average over all the people. Yeah. So I would need to do that in order to estimate this quantity. But this is like what I want. Okay, thanks. Yeah.
And how to cultivate the root cause analysis? Same thing.
Root cause analysis.
For example, have a device have 100 parts, right?
Yeah.
Have 100 sensors. So when something wrong, we call like find the root cause. Something like it's the same thing.
Yeah. So I think there's what you can do is so if you want to find the root cause, so you're saying like you have this like complex system,
yeah,
and something goes wrong.
Yeah, for engine, right? How big engine have a certain sensor, right?
Yeah.
Something wrong.
Yeah, so you could do it like this, right? Like if you had like sensors, you could compute like the probability that some particular thing broke given the various sensors. So I guess with diagnosis, you don't necessarily need to know the causal effect, but if you want to estimate like the effect of an act, like given that these sensors read something like what's the optimal action to fix it, then you would need the underlying causal structure. So for example, let me think of a good way to. Yeah. So I know like So okay, let me put. I think you could use like the if you had the structure, you could use the graph to kind of do inference that probability that this particular, maybe it's a latent thing. You don't actually observe it, but you have sensors for it, right? You can you can do a latent variable analysis to try to estimate that. Yeah. Okay. Any other questions? Yeah.
So how do you know that the causal model is better? Like, does it necessarily improve your, for example, let's say you build just a regular out of the box neural network kind of predictor with all of your variables, no causal model. and then you do a second analysis this time, trying to identify the causal model. You do the same process that you just outlined.
Yeah.
Do I know that my accuracy or my performance of my network will necessarily increase?
Okay, so I think, so your question is if you were to just, so I think part of it would depend on the task, right? So if you have a causal query, then you have no guarantee that whatever your neural network learned is causal. So you can imagine a situation where, like, let's say we go back to this example, right? This example here. So if you were to train a neural network, it could maybe do a really good job predicting recovery, but you wouldn't know, like, based on the drug. And so maybe it's like a super complicated drug where there's like 50 million different ways to take it, and like the relationship between those 50 million different ways, and there's like many different ways you can recover. Like that could be like maybe if it was like highly nonlinear relation and very high dimensional relationship, a neural network could learn that association, but it would just learn this association, including the confounding. So it wouldn't tell me, like, if I were to actually take this drug in this way, like what's my probability of recovery. So yeah, so that's kind of the idea. The neural network can learn a very, very complex association, but it doesn't guarantee that it's causal unless it's licensed essentially by the underlying structure, right? So yeah, that's it. But people do use, so there's two sides to estimating causal effect, right? First, you have to identify the causal effect, which establishes the relationship between the causal quantity and the probability distribution. It's basically you're equating the causal quantity you care about to the probability distribution. And probability distribution is something you can estimate from data using standard machine learning with statistical inference. So people have like used neural networks, for example, for instrumental variables. They'll say, like, if this Z is an instrument, here's a way that you can use a neural network to learn a really complex like causal relationship. But you need to have that underlying like causal knowledge saying this is an instrumental variable. Otherwise, you don't know that you're learning a causal quantity. You might just be learning something predictive. Yeah. Yeah. Thanks.